Hi, today I'm going to introduce Sherlock-Q and our team members are Golder, Kai, Binet, and Yuha. Okay, let's begin. So why did we start this project? Nowadays, people use AI like ChatGPT in their everyday lives. But the problem is that a lot of AI is based on neural networks and their sizes are getting larger. Then what we can do is finding hardware-friendly neural networks, which is the main goal of Sherlock-Q. Then what are some benefits of dedicated hardware compared to general hardware like a CPU? With the dedicated hardware, we need a lower power, memory, and storage to operate AI services, and it gives higher performance like latency or throughput. There are some techniques to efficiently implement dedicated hardware like quantization and pruning. Among them, Sherlock-Q focuses on quantization. Then, what is quantization? For example, in the decimal system, if we have a floating point number and want to get an integer number, we can simply blow away the decimal part of the floating point number. In terms of hardware, floating point number is usually represented as 30-bit, and integer number is represented as 8-bit. Since most raw neural network consists of floating point numbers, when we can quantize all floating numbers into integer numbers in a neural network, we can roughly downsize the neural network by 1/4. Unfortunately, quantization is not an easy job because there are lots of design choices. The process of finding design solutions from a design space is called design space exploration or DSE. What Sherlock, which is a modern model of Sherlock-Q, does is minimize total consumed time for DSE and show trade-off relationship such as size versus accuracy, which is called Pareto graph. Here's an example of Pareto graph. Normally, the closer to the origin point of Pareto front is, the more efficiently it handles trade-off. But what's the Pareto front? On a Pareto graph, each axis stands for a design objective such as model size or model error. While exploring design space, we can obtain each model's result and mark that result as a point. For example, on the top left corner, the point came from a non-quantized model that has large model size and low error. Among those feasible points, there are border points that are close to the origin point. We call them Pareto points. Lastly, a curved line that connects those Pareto points is called Pareto front. Now we can introduce our frame of Sherlock-Q. Sherlock-Q is a software tool to suggest design choices for dedicated hardware. You can use Sherlock-Q with the GitHub repository introduced here. Sherlock-Q reduced the total amount of time for quantization DSE and shows us a Pareto graph about the DSE performed. A target neural network is a simple MLP model with 3 hidden layers, and the input for Sherlock-Q is quantization configuration. Firstly, Sherlock selects some quantization configuration for initial training. Once it finishes the initial training, we can get some model sizes and model errors, and Sherlock can calculate the Pareto scores with this information, then select the next quantization configuration based on the Pareto scores. After some amount of DSE, we can collect all results, and Sherlock-Q finally shows a Pareto graph. Here's our result, and Sherlock-Q performed only 15% of DSE and found Pareto front very well. With the help of Sherlock-Q, we can now significantly reduce the time consumed for DSE, and hardware designer can easily select their design choices among Pareto points. For example, if one design allows only extremely small size with a bit of error rate, then the model of point 2 will be the preferable design choice. We also compare our result with previous research. It shows that our Pareto graph is comparable. Note that Sherlock-Q's main goals are reducing time consumed for design space exploration and showing Pareto front. Improving each model's accuracy is orthogonal to Sherlock-Q's main goal. So if we improve the training method for each model, then Sherlock-Q can suggest a new Pareto front closer to the origin. For future work, we can try out more common neural networks like CNN or transformers, and we can explore more fine-grained bit widths which are commonly used in dedicated hardware. Finally, we can also try other quantization methods like DFP or mini-float or mixed precision. To sum up, Sherlock-Q does quantization space exploration, which enables the efficient implementation of dedicated hardware. Thank you.